Welcome back to the course on superconductivity. Today we're going to talk about coupling loss. In superconducting magnets, there is 4 sources of loss, classified in 2 groups, DC and AC losses. The subject of today's video is the coupling loss, the 3 AC losses. Coupling loss is one of the AC losses and happens during AC operation when 2 or more superconductors are close together with a conducting material linking them. You can see on the left-hand side a cross-sectional cut of typical composite wires. The superconducting wires in gray are very close to each other, and the matrix being made of copper creates favorable conditions for coupling loss to happen. For the same reasons, stacking HTS tapes in the same manner as shown in the right-hand side picture will create great conditions for coupling loss to happen. For now, we have only talked about the conditions for coupling loss to happen, but not how. When a change in magnetic field happens in a conductor, an electromotive force will be induced, following Lenz's law. If the change in magnetic field is high and the superconductors are close enough, they will get coupled. Basically, the screening currents are coupled between the superconductors in a way that a current flows between each superconductor through the matrix, like in the figure on the left-hand side. In this figure, an increasing magnetic field is applied perpendicular to the wire. If we look at the magnetic field in this plane, we can see the screening currents are added up to cancel the magnetic field. Comparing with the figure where the superconductors are not coupled, one could say that the coupled state should not be stable since it looks like a higher energy state, and this is right. It will eventually decay to the uncoupled state. However, the characteristic time for the decay can be very long, ranging from hours if the matrix resistivity is high to years. In the same way, stacked superconducting tapes can get coupled, though they tend to be coupled when a change in magnetic field happens in the winding direction. To prevent coupling loss and reduce the decay characteristic time, the wires are twisted as shown in the picture at the bottom. This reduces coupling losses since every half turn, the wire or tape feels a changing magnetic field in the opposite direction. To better understand this sentence, let's look at these 2 images. On the left-hand side, we see the cross-section cut highlighted in red on the right-hand side. If we use this blue filament as a reference, we see that every half turn it goes from one side to the other of the cable. However, the magnetic field being still in the same direction, the coupling current is inversed from the perspective of the filaments. In other words, the coupling current is inversed every half turn so that the characteristic coupling time decreases. The characteristic coupling time, denoted tau, is defined as the time the cable takes to go from its fully coupled state to its 36.8% coupled state. Having a short coupling constant means that the filaments are going to be coupled for a shorter amount of time, which means less losses. To conclude, by definition, coupling loss is one of the mechanisms causing AC losses. It happens when 2 superconductors are close enough so that their screening currents get coupled through the matrix. Coupling loss, being one of the AC losses, can have a significant impact on the stability of a superconductor during AC operations.